So this integral image itself is actually a nice concept, and how it works, right. So the idea is that you see, for a SIFT, right, what we had to do was we had to have different octaves, right. Within an octave we had to have, right, different scales. We start with sigma, then we have k sigma, k square sigma, and so on, right. And our idea was that then we can go to the next octave, and so on. That was the way, right, we were implementing it. And then the reason why we said we wanted to go from one octave to another was to simply reduce the size of the image, so that we can do things faster, right, because searching in one resolution, the highest resolution for all the scales, is going to be a time consuming affair. So we said we will downsample, blur and downsample, and then on that, right, you build another octave with different scale, then go next octave and do like that, right. Now what you can show, okay, using this integral image sort of notion, is that if you try to do a convolution sum, right, which is what you do, right, I mean, that is a convolution is independent of the size of the kernel, right, which is like kind of a big thing. For example, if I have a convolution that I have to do a 1 cross 1, compare it with actually a 3 cross 3, compare it with a 5 cross 5, 11 cross 11, it looks like I have to do a lot more work, right. That is one of the main things. So if your sigma goes up, then your base, the spatial support goes up, then your computations go up. So the claim is that using this integral image, it's totally invariant. Whatever size you give me, a 99 cross 99 kernel, I will take the same amount of time that I would take for a 3 cross 3, right. That is the claim, okay. And once you can make that happen, right, then you no longer have to kind of look at different octaves and all that, right. You can simply run it through, because you really don't care now. I mean, I can have as big a size a filter that I want, because that was the reason, right. We said that when there is a blob and you want to actually match it up, right, and the blob is big, right, then you have to have a big sigma, right, in order to actually fit that blob, right, and whatever scale it matches, that's when it will flare up or it will fire. But then the problem was that you had to then create a kernel of that size, do a dog approximation to that and do it. So all that meant that you had to spend so much time in doing these calculations. Whereas in an integral image, it looks like you can have a 5 cross 5, and then you can go to 40 cross 40 and then not bother. In both cases, right, the computational requirement is the same. But how it happens, right, we will see next. Okay, so the idea of an integral image. So what is so the whole thing, right, revolves around this. Okay, which is why I wanted to spend some time telling you, what this is. So the evaluation using integral images. Okay, so the key point is this: the evaluation using integral images requires the same number of lookups. In fact, it's more like a lookup calculation, okay, regardless of this image scale. Thus removing the need for a pyramid, thus doing away or removing the need for a Gaussian pyramid. And you see, in those days, right, this led to a 5x factor speed up, but I'm sure, right, it's much more. No, maybe if you look up now, right, there must be more recent implementation which claim probably even more. Okay, so this integral image comes from this Viola Jones paper, 2001. Okay, but these, of course, but these people did a lot more work after that to show, right, how it can be done. Okay, let's not talk about what is an integral image, right. So right, given an image I, its integral image let's call me suppose I call this I sigma, right. That's the sum image, or integral is like sum, right. So I call it summation. So I sigma. Okay, now in at x comma y, is equal to double sum I equal to 0 to I less than or equal to x, j equal to 0 to j less than or equal to y, I of I comma j. What does that mean? Suppose right, let us just take one example. Okay, these things are best explained with an example. Okay, first of all, I think we'll first kind of take an example. Suppose some random example, okay, which I've taken here. This is like 4 cross 4. Okay, and the entries are 1, 3, 2, 4, 5, 2, 1, 6, 4, 6, 2, 5, 1, 4, 1, 1. Okay, this is my I. Okay, and I want to write up my I sigma now. I will tell you what is the utility of this I sigma. So let me just draw the same grid. Okay, what will be the first entry now? If you go by that I of x comma I sigma of x comma y is okay. So 1, next 4, next 6, next 10, right? Then when you come to 5, you can only go up, right, because you have to have I less than or equal to x, j less than or equal to y. So you have to stop at 6. When you go to 2, no, 2 plus 3. See, when you go to 2, right, you can go up, you can go left, right? You cannot go spill to the right of 2, because I less than or j less than or equal to y. Yeah, it's just a top square. Yeah, so it will be 3 plus 5. What is that? 3 plus 2, 5, 11. Yeah. Do you follow? And then when you go to this 1, you can go like 1 plus 2, and so you just add 3 more, right? So it will be 14. Then you add another 10, that will be 24 for 6. When you come to 4, it will be 5 plus 4, 9 plus 1, 10. Then the next, when for 6, you add the whole column above 6, including 6, right? Less than or equal to, okay, it does not exclude your x comma y. So 6 plus 2, 8 plus 3, 11, right? 21, right? Then 21 plus 23, 26. Then 31, 41. Then 1, 11. Then 21, 23, 26. Then 27, 29, 30, 32. Then 32, 33, 38, 48. Something like this, right? So 1, 4, 6, 10, 6, 11, 14, 24, 10, 21, 26, 41, 11, 26, 32, 48. Okay, now for the time being, right, suppose we just leave this off. Okay, now if I were to kind of take actually a grid, okay, where I kind of sum up the areas, right, in this manner, and suppose I am interested in some shaded area here, right, at every point, right, so for example, right, imagine that you are actually computing the area just the same way, right, whatever is above, right, all the way to the top and all the way to the left. For example, right, if this is my point D, then the area, right, that I have computed when I am at D is all of this, right. So all of, I don't know, whatever color you want to show, right, all of that, okay. Whereas if I say that my kind of point is A, then what will be the area that I have covered? That area will be something like this, right, it will be this area that I covered. And then if I say that I have got a point B here, can't even see that, let us say B, right, then B will be all of this, B will be all of that, right, is that correct? And then so let's say we have another thing that is C, which is here. What will be C? C will be all of this, correct. Now if I was interested in the area under A, B, C, D, right, then what would I write it as? So if I am interested in the area of A, B, C, D, that is that shaded region, right, let us say whatever this shaded region that I have here, okay, this guy, the shaded region, I want the area. So what would you do? You will say D, right, what do you, you can do it in whichever way you want, maybe, right, maybe you can say D minus B, but then if you knock off minus C, you would have also knocked off A then, right. So, you should add A back, otherwise you would have knocked off A. So, you can say plus A, right, or you can say A plus D minus of B plus C. Why is this important? Why am I saying this? It looks like some, like elementary 4th class stuff, right? But but why is this irrelevant? Do you see where I am going? Even though this looks,
What is that rectangular?
yeah, that's like the right area under area right within that rectangle. That's the area within that rectangle.
No, I'm asking what is that rectangle itself?
Oh, the rectangle itself, yeah, exactly. So, which is why, right, if you actually come back to your problem, okay, which is like I have an image, okay, I have an image and I have actually a box filter, okay. When I do a convolution with actually a box filter, isn't it like, see, for example, right, I mean, if I keep my box filter somewhere, okay, let's take a 3 cross 3, okay, if I keep a box filter, what am I doing? I am simply summing up all the elements under it, right, because all my weights are 1. I don't have to weight anything. It's simply whatever is under it, add it up. Right? If it's a continuous case, it's the area. In this case, it's just a sum of all the numbers under it. Now, if I have a larger kernel, let's say, right, this is like 15 cross 15. Again, right, if I doing a convolution with the underlying patch is equal to simply adding up all the right elements under it. Now, can you kind of relate this to this I sigma? See, we know that in I, right, if I wanted to do a convolution with I can take a kernel like this, which is our old fashioned way of doing things, right. I can take a kernel, move it all over, but that is the same whether you whatever kernel you have, right, or Gaussian also you would have done this, but then should we be doing this when we have a box filter with us? Right, it looks like it's a very inefficient way to actually do it, because after all moving it all around is simply equivalent to adding up the right elements under it, and I sigma is actually doing that, right. So, now suppose I ask the following question, right. See, suppose I have a 3 cross 3 kernel, right. So, we have a 3 cross 3 kernel, okay, and I center it here. Okay, now, okay, wait, let me remove, oh, what was that number, by the way, 2, Let me take this example that I have here, 216, 625, okay, 41, okay, fine, like that. So, okay, so it turns out that it's the same example, okay, and I am actually centered here, okay. So the point is, right, if I had done a convolution, if I had taken this 3 cross, it is all ones, right. I mean, for the time being, ignore that factor outside. It can be whatever, okay. I don't care, it's just a uniform number, I multiply, right? Once I get the area, multiply it. So, if I just look at it, right, that's an arrow, okay, that's not 21. So, if you look at it, it will be just to, what is it, 9 plus 6, 15, 17, 22, 26, 28, right, that is what I should get if I do a convolution for that pixel which is at the center, right. So, I should ideally get to see 28. Now, I want to show that you can actually do precisely that if I from this is I sigma image, okay. Now the sort of a convention, adopted convention is this, okay. In order to be able to move wherever you want, so what is normally done is you append one more row and column and put them as zeros. Okay, I mean, in this case you don't need, but then if you are at the border, right, you might actually need it. Okay, now I again include these values 1, 4, 6, 10, 6, 11, 14, 24, 10, 21, 26, 41, 11, 26, 32, 48. Okay, now see, I mean, if I were to locate this 2 here in this I sigma image which is appended, which is an extended I sigma image, where is this 2 now? 2 should correspond to whatever is the area that I would have gotten at 2, no, that will be like 10 plus 3, 15, 21, 26, right. So, it means that, right, it is here, right, right, 2 is right there, and then of course and then you have these 3 numbers that, for example, for this 2 it would have been 11, for this 6 it would have been 24, and so on. Okay, now I am going to indicate to find this convolution, right. I'm going to call certain things as A dash, B dash. So I'm going to say this is A dash, which is across this 11, and above this 24 I'm going to call this at B dash. Left of 21 I'm going to call as C dash, and this 41 this not I mean left of 10, left of 11, left of 26, sorry, hey, this is the problem with these things. Can you tell me what was this number? 6 and then 21, na? No, kya ho gaya? Something 10, it was 10. Okay, so A dash here, C dash here, C dash here, B dash on top, D dash is this guy 48. Okay, and now I am going to do this A dash plus D dash, right, which will be 1 plus 48 minus B dash plus C dash, which is 24 plus 11. I have like 49 minus, hey, no, what happened? I think I made a mistake somewhere. Wait a minute. 48 plus 1, oh, 10, yeah. You should have, no, it's not 24, right? This is 10, no? B dash plus C dash. So this should be 10 plus 11, which is C dash. So 49 minus, what is this? 21, right? So that is equal to 28, which is this value. Okay, now it's easy for you to show that if you take an integral image, and if you actually, if you now call this as A dash, B dash, C dash, D dash, then the convolution for that pixel which you are examining at 2 can be obtained by simply doing this A where your convention is A dash, B. See, you can also do it by using the whole image and so on. I mean, there are multiple ways to do it, but then one of the most common conventions is this, right? Mark your A dash, B dash, C dash, D dash like that. Now, why do you think, right, this is nice? I hope that you need not
do the looping every time.
Not just looping. Suppose I gave you 7 cross 7, you still have only these 4 numbers to compute.
Yeah.
Right? If I give you 11 cross 11, I am just taking a small example.
Again, image size.
Yeah, and once just at one time, right, once you have computed sigma, I can run any size of filter on it now, right? I mean, I can use my scale whatever I want. I mean, if I want a 50 cross 51 cross 51, I can run it, because again because my I sigma I just have to compute once, right? And then whatever I want as a sort of a convolution, whatever filter size I want, I can simply arrive at it using a simple whatever, right? What is this? This is like 2 additions and one subtraction, right? That's all I need. And with that, you can actually compute a convolution of whatever size you want, right? That is the strength of this integral image, and of course assuming that you have a box filter, of course, okay. So if that has sunk in, and this you can extend to anything, okay. By the way, it is not restricted to a 3 cross 3 and all. I mean, as long as you actually you have a definition. For example, you can have a row filter, you can have a column filter. Every time if you follow the convention, it will all work. You can have a 2 cross 2 filter. It does not have to be exactly a 3 cross 3. Now I took a 3 cross 3 because it's easy to understand, but it doesn't mean that this will work only for 3 cross 3 and all. Okay, you can take even sized filters. Okay, even for that it will work. But anyway, right? I mean, for the time being, right? Let's not actually worry about. I mean, if you want it, you can just check out one of these. Let us say that if you just wanted to, just for example, right? Suppose we take 2 cross 2. Okay, let's take this. Okay, and suppose I say that, right, I'm actually centered here. Okay, I mean, again, see, the only problem with this even is that you will have to tell where the center is. If you take that, right, then a convolution, right, will be what 6 plus 4, 10 plus 1, 11, right? 11 is what you should get. Now, where is this 2, right? You've got to locate this 2 here. So, 2 is sitting at 11, right? That's what it is, no? So, 2 is sitting at 11, and then 14 will be this 1, and then 21 this, right? So, what will be your A dash? A dash remains as, what was that, 1, right? A dash is 26? No. 1. A dash is 1, right? And then B dash will be 10. C dash will be 6. and then d dash will be 14. No, sorry, d dash will be 26, right? D dash is 26. So now you do know a dash plus c dash, sorry, a dash plus d dash, which is 27, minus b dash plus c dash, which is 16, right? That is equal to 11. What should it be? 4 plus 7, 11, right? So whatever it is, right? As long as you follow the convention correctly, you can do, right, any size filter, any even one dimensional, anything will work. Okay, now having right, once we know this, right, that right, this is the power of the integral limit. Now, right, this by itself is not enough, right, for us. Okay, so what they do is, they go ahead, and here is where, of course, they have done a lot of work, right, in trying to find out what would be an approximation, what would be a box filter approximation to your to a log that you need next, right. Now, this involves, a lot of, so this involves a lot of analysis. We will not go into that, right. We will simply say that in fact, they have to compare a linear sort of, a Gaussian scale space with respect to a box filter scale space and find out where the approximation happens the best and so on. The studies show that sigma equal to, so for example, if you have a sigma equal to 1.2, okay, which is where they start, in fact, that's the smallest sigma they actually start, okay, this one box scale space, and for that, right, you get actually a 9 cross 9 filter. Okay, so let me say 1, 2, I don't know, 3, 4, 5, so 3, 6, 7, and then let me put 2 more here. Okay, 1, 2, 3, 4, 5, 6. So, okay, well, maybe, right, why don't I just show that instead of right, doing this? I think oh, I don't think I copied the slides today. Okay, so the way right, this looks like is as follows. So the middle, so here and all, right, it's zeros. Okay, these two columns. In between, it's got like 4 ones here, and then again these two are zeros, and then this repeats till this, and then you have like minus 2, minus 2, minus 2. Okay, and then minus 2, minus 2, then again minus 2, minus 2. I think there is only 3, it looks like I missed a row. Okay, there should be one more row. Then this is like, anyway, I'll show you the slide tomorrow, right, where this is all available. So, and then these are like ones, okay, and then again, okay, I think I'm kind of missing some rows and columns. Okay, it's okay, and as long as you understand what's going on. But then, right, the kind of key is going to be next, right, what I'm going to ask you, and this whole thing is 0. Okay, this is all zeros on the left. Okay, something like this is what it looks like. Okay, this is what they show to be a good approximation to a log at sigma equal to 1.2. This is actually a 9 cross 9 filter. This is what is like your dyy, and then a transpose of this will be your dxx and so on. And similarly, right, they have a 9 cross 9 kernel approximation for your dxy. Now, see, the earlier case was that we had all ones, it was easy, right, we saw that, right, we could do it, but then finally, right, I want an approximation to the log, right, I don't have box filters, right, box filters can't approximate a log. So when I go into approximating a log, this is the filter I get, which is a 9 cross 9 filter. Now, can I still use that integral image idea, even though I have a filter like this now? How would you do that?
No, but it is space variant.
Yeah. Yes. Well, not space variant. Actually, that's not strictly correct. Space variant, you mean that the numbers are not uniform. That's what you're saying. It's not uniformly just one number all over. That's what you mean, right? It's a space invariant filter. This is a filter that get applied everywhere. It's not a space variant filter. It's just 9 cross 9, right?
But
The entries are changing.
concept that we used that
Yeah.
in the I sigma was we had some special orientation.
No orientation, all ones.
No, since everything was once,
Ah.
we were able to probably subtract it.
But I'm saying that I can still kind of write, I can still do that here. What should I have to do?
A combination of both.
Huh? I don't want to do that. I want to use my integral. No, I don't want to prompt that answer. Huh? Go ahead, do it. Okay, so what you are saying is if I have minus 2, I can actually remove that minus 2 out and I can operate it later. Is that what you are trying to say? See, I want to do all this operation using just the integral image. I don't want to write anything else.
Using that double sum.
Yeah, just that. Okay, that is the only thing I know. Okay, it's like somebody who is trained only to do that, right? I know to compute, use I sigma. I know to do. That's all I know. Okay, go back and think about it. We ran out of time. I didn't realize. Okay.